Hey everyone, welcome to another video. In this video, I'm going to be talking about 4D mitochondria analysis. So here's a situation that some of you who do 4D mitochondria analysis or any sort of 4D analysis with microscopy images, you would be aware of. So here's an intensity image, and this is a 4D volume. Okay, so this is what it looks like overall. I have these centroids drawn over there so that we can track individual mitochondria and see how they are moving around. But even more importantly, what we want to be able to do is we want to be able to understand the dynamics of the mitochondria relative to each other and to their endpoints, but also the quantity of these mitochondria, and then how many times, for example, per cell or individually, are the mitochondria undergoing fission and fusion. Right. So these are the metrics along with the volume, the area, any sort of other like morphological feature that you might be interested in. So these are the questions that anybody who is doing mitochondria analysis would want to know. But somehow doing that sort of analysis becomes extremely challenging and can end up taking 5 to 6 different programs and then 2 or 3 different plugins in ImageJ to be able to just achieve some sort of a spreadsheet that contains the metrics that one might be interested in. And then, not to mention, after you're done with the programs, you still have the spreadsheets, which also need another set of spreadsheets to be able to finally get to some sort of an outcome that is understandable by a human reader. So, long story short, somewhere in the middle of all of that workflow, you stop being a scientist, you start being a file formatter. You start to learn how to format different files so that you can get your analysis done as efficiently as possible. And there's an even bigger and maybe a more subtle problem. And that problem has to do with how expensive this can be. The four-dimensional analysis, specifically in terms of mitochondria dynamics, can be extremely expensive. And I'm not just talking about the cost, I'm talking about the time that you invest into it. I've watched some really good labs postpone their analyses because of the software complexities and the workflow pipeline chaining that comes along with it. So several years ago, I got fed up with the pipeline chaining that I was doing to be able to achieve mitochondria analysis. And I ended up developing what you're seeing in front of you. So what I will do is in this video, I will show you the workflow that I use with MitoFlow to be able to achieve certain amount of analysis that I like to do for my images. And then I'm going to use a real world example. So instead of using this sort of a synthetic data that I have in front of you, I'm going to use a real world example of a real data set that comes from MitoTNT. Okay, so they have a test data. This is a light sheet microscopy image stack, and they have provided this test data on their GitHub repo. So shout out to them. The credit for the image belongs to them. So I'm going to use this image to showcase what MitoFlow can do and what you can sort of expect to get out of it. Let's go ahead and get into this. So first things first, if you get any sort of repository, I'm going to first delete these old files that I have. If you get any sort of repository, like for example, MitoFlow, please navigate over to the extracted folder, and then you're going to install via pip. Oh, before I even do that, let me actually make sure that I cover this. You're going to need to create an Anaconda environment. I have plenty of videos on my channel here that show you how you can create a new Anaconda environment. If not, please Google it. And I also have those instructions on the README documentation. Please make sure that you look at those. So create an Anaconda environment and then activate it. And then what you're going to do is you're going to pip install the repo into that. Instead of me covering individual modules, I'm just going to give you this installation command. So pip install in quotations, double quotations, put a period, and then in brackets put all, and then you can just enter. And this will go ahead and install everything for you. Now, in my case, I already have everything installed. So here you will see that it tells me requirement already met. And I'm going through this as a sake of just demonstration. So once the MitoFlow repo has been installed in that Anaconda environment that you created, you're going to launch the MitoFlow GUI. So if you are not going to be using graphic user interface, then you don't need this video made. So, but for everybody else who is not comfortable using the command line interface or doesn't like typing things into the command line, please use the graphic user interface like this. Okay, so this will pop up. It's made with PySide 6 and uses Napari for visualizations. A lot of different open source projects have come together to make this happen. Before I get into this, a few choices shape everything that follows. And one of the choices is that this workflow is all CPU driven. So because it's CPU driven, depending on how big your images are, how many mitochondria you have out of the segmentation of the cells that you're going to use, your CPU analysis can take anywhere from 3 to 4 minutes or slightly longer. Okay, so first things first, I'm going to go ahead and create a project. I'll just call it test, and then source video. Like I mentioned, I'm going to use the MitoTNT's source video, which is, I have it here instead of the MitoFlows, which is my own image. I'm going to use the MitoTNT's image. And then I'll create a new folder called YouTube just to keep everything contained. That is now going to be the analysis output folder. So taking a look at this file, we can see the shape of the image that I've just brought in. And then over here, we can set the voxel spacing. So for sake of this demo video, I'm not going to change these voxel spacing. And I'm just going to run through just using 1 by 1 as the voxel spacing. So then I have to click a few buttons here just to make sure that I have looked at these numbers and confirm that these are correct for the image that I'm using. So let's go ahead and draw the cell boundary and see what the cell looks like. So here we have a maximum projection of the cell. So on the right top here, it has this maximum projection checked. I'm going to switch this over to individual slices. And then after that, I'm going to switch it over to 3D volume so that you can see what the volume itself looks like. And it's actually a 4D volume. So we can see what happens over time, how the mitochondria are moving. They're very dynamic. Okay, so this is the raw TIFF file. Okay, so a couple of things I need to do. I need to put a bounding box around the cell. If you have more than one, for example, more than one bounding box or more than one cell, you can put multiple types of bounding boxes. So here, for example, I've put that, and I'm going to make just a big one like this, or anything will work as long as you can encapsulate your cell within that boundary. And then after you're finished, you can simply hit apply cell boundary, and it's going to go ahead and apply it around the volume that you have. Okay, so I'm pretty happy with this. I'll just go ahead and save and return. So that is now going to be the ROI of the cell. If you have more than one cell, feel free to draw more than one ROI for each one ROI per cell. Okay, so once that is done, let's move on to saving the project. And then we have to make sure that we select appropriate thresholding parameters. I've already fiddled around with the thresholding parameters, and I have landed on a few that work really well for uh, this particular 4D volume. So those are the ones I'm going to select over here. For the local scale, 0.5 worked really well. And I'll go ahead and bump this one up to 5 frames for the temporal threshold, and everything else I will keep the same. The segmentation just finished. I'm going to go ahead and go to segmentation audit. Okay, so just out of curiosity, I'm going to turn these on and off just so that I can see what's happening and what the segmentation sort of gives me. Go ahead and turn these androids off. They're kind of distracting me. So I'm going to go ahead and say that this is not a bad segmentation. In certain regions, I can, of course, improve this by tuning the parameters just a little bit more. But from what I can just quickly check, they don't look bad. So this is again segmentation, and we haven't done any sort of analysis with this yet. So let's go ahead and do that next. Oh, by the way, any window that you open, you can of course come here to the render images and movies. And as you're panning around, you can set your keyframes so that the video can be generated using the keyframes that you're selected. So the movements are going to be captured, and you can even play this video and capture the temporal dynamics as well. But that feature is in there too. I'm going to go ahead and jump out of this one. Let's move on to doing the analysis. And this is where I'm going to use the same cell mitochondria edge-to-edge proximity as well. For my personal case, I was very interested in the proximity of mitochondria to certain contact surfaces. That can include ER, that can include Golgi, it can include mitochondria to mitochondria contact, and the proximities of mother mitochondria and daughter mitochondria, and so on and so forth. So I built this system in for myself to be able to achieve that. And this is something that I had a really hard time doing with other softwares. Okay, so the analysis itself, depending on how many mitochondria that you have in your segmentation, this can take anywhere from 2 to 3 minutes or slightly longer, depending on how many mitochondria the program has to compute for. And it's going to also calculate the surfaces and the meshes for the mitochondria proximity, so that I can have that information for myself as well. And then after this is done, there's going to be we're going to move on to the explore and verify side of the analysis. So let's go ahead and wait a little bit for this. The analysis has just finished. I'm going to change a few things here so that the visualization matches what I expect to see. I'm going to change these colors to what I like. I will keep the persistent track identities, and some things that become very apparent are that failure modes, especially in the dynamic analysis of identities, because each individual mitochondria, as they're splitting and merging, they tend to take on different identities. And if a tracker swaps the names of the two mitochondria, or in this case, the index of the mitochondria gets swapped, the velocity can end up being wrong, the displacement can end up being wrong, and the event call can also end up being wrong. And the result can still look perfectly fine at a quick glance, but between consecutive frames, the program builds candidate parent-child pairs from voxel overlaps and calibrated distances. Each pair receives a cost that combines overlap through an intersection over union term. And in fact, I'm not going to go over the detail of the math here, but the documentation will provide more on that. But the analysis is done. We got about 7,858 objects, one selected cell, persistent tracks 2,858, 890 event candidates. So events are fission fusion events. Accepted endpoint vectors 2,832. So I'll show you what the vectors mean here in just a bit. So let's go ahead and open the Data Explorer. And this is the part of MitoFlow that I really like for myself. I really am a visual person. I wanted to see what was happening and how I could verify fission and fusion events manually by actually seeing things happening. So here's the raw, and then I'm going to move on to the stable tracks. So now these are the stable tracks. Anytime a mitochondria changes and merges into another one, the color changes. Okay, so all these things that you're seeing here that are changing the colors, there's an event happening, either fission or fusion. The color change is representative of that event. It's a quick at a glance sort of a thing. And then, of course, we can look at the endpoint modeling, and these are vectors drawn at the endpoints, and their direction and the arrow length tells us the both the directional change that is occurring instantaneously, and then also the magnitude of that change. I'm going to go ahead and play this one out so you can see this for yourself. Okay, so I'm going to go ahead and slow this one down because otherwise it's going to be too fast. Let's go ahead and back up a bit. Here you can see that these two have very high magnitude for the change, relative change. So the arrow is representative of that relative change. I'm going to go ahead and move on to the remodeling heat map. This is another way that you can at a glance view the dynamics of where the cell is most active at any given time. Okay, so you can very quickly be able to tell and see where the cell has the most amount of activity at any given time. The mitochondrial networks, and anytime that you click on the networks, in the backend, it's going to load in the network. So it can take anywhere from 30 seconds to 45 to a minute or two, depending on your hardware. And then when the networks load in, you will see there are two different types of nodes. These cyan ones, and of course you can change their colors. The cyan ones are the endpoints. So these are going to be the edges, the beginning and the end of the mitochondria, for example. And then at any point you need more information, please go over here to see how to read this. And I have some tooltips listed over there. You can change the colors from over here, where there's a collapsible options here on the right. Okay, so each one of the nodes here is representative of some sort of a fork happening in the mitochondria. Okay, so I'm going to move on from this, otherwise I will take forever. The last thing I'm going to show you is the event verification. And there are lots of options here that you can fiddle around with, specifically like the extension and retraction field, for example, right? You can turn those on and off. Okay, so there are a lot of these individual visualizations that I have because I need to be able to confirm. And the best way to confirm certain events that are happening is through visual verification. And if you have the background selected properly, you can also see the index of each of the endpoints. Okay, so I'm going to go ahead and close out of this one. Let's go over to the review temporal event. And this is where things get really, really interesting. And you can visually verify the fission-fusion events. Okay, so a couple of things to say over here. The middle, the bluish looking circle is the event area. So that is the area within which, or volume within which the event is occurring. The surrounding spheres that are in this orange yellow color, those are the mitochondria that are either undergoing fission or fusion. Anytime you want to change and recenter your event, you have a list on the right side where you can click on this. It will take you to that event, and you can see what type of an event occurred in that space. So for example, looking at the event 11, it says fission. Fission is happening. So if I go back one frame, we can see that this mitochondria is a single entity. And if I go forward one frame, it has split into two, and that is also represented here by the color. Okay, that's the event boundary. That's where it happened. And now I'm going to put the spheres around for each one of the objects. And as I'm panning, you can see both of those show up. And then this is the track over which this event has occurred. Okay, so you can go through these for at least a handful of these events, and then see where if there are any mistakes. So you can of course correct them. You can accept you can say here verified, reject, clear, or questionable, so that you get a metric out, a sort of a ratio of how many correct to incorrect events did the program detect, and then you can report those if you need to. But this for me is very handy because I am a visual person. I want to be able to pan around and see if the events are truly happening. There's also nearby tracks that you can turn off, because if there are any nearby events happening, you will have the proximity of those events. And in some cases, you may actually want to know. Anyways, in my case, I wanted to know. So I have that designed in. Okay, so yeah, I'm going to stop right here. The video is getting quite long. But this is MitoFlow. So everybody who has been emailing me, I've heard you. This is something that I've been using for a little over a year now, at least. And this has been in development for over about 2.5 years or more, probably at this point. But I'm finally putting this out. This update is going to be on GitHub soon. Link is going to be in the video description. If you want to check it out, feel free to do so, and leave me your thoughts and your comments. Let me know if this program can help you. If you run into any issues, let me know. You can open up a issue in the GitHub to let me know if you run into any sort of problem. From the testing that I've done, I've tested it on 2 different computers, and for both cases it has worked. Okay, so with that being said, I'm going to go ahead and stop right here. Again, leave me your thoughts and your comments, and click the like on this video if you find this to be helpful, and let me know that this was helpful to you. Thank you so much for watching. See you in the next one.